Hey guys, this is our Hurricane Makeup Lecture number 3, intended to make up our Friday lecture. Few comments before I get started. One, this should close up our covering section 7.2, so this is the last day of that section. Another comment, if like usual, if you guys are more interested in reading than you are in watching the video, there is a PDF associated with this set of notes posted to Moodle. There is one additional exercise, I think, towards the end of the notes, though, in this video than there is in that file. Also, a final closing note for those of you guys that may be skipping around the video or such. There is a quiz on the last page of this video, so do be aware that that's a thing. Make sure that you see that and that you turn it in at some point whenever we get back. If it has to come in late, that's totally fine. Anyway, let's go ahead and get started. Section 7.2b on trig integrals. Remember last time, if you watched the last video, you should hopefully have recognized there were two tricks that we went over in that particular section. We were taking a look at both, integrals that were written in terms of products of trig functions, either the case where there were odd powers or the case where there were no odd powers and everything was even powered. In the case that we had odd-powered trig terms, we used the Pythagorean trigonometric identity, so that's going to be this guy right here. If I could actually underline it. Pythagorean trig identity right here. That's what we use whenever we see odd powers to help us rewrite things. On the other hand, if we were dealing with an even power only integral, we wrote stuff a slightly different way. I'll scroll down a little bit to highlight the formulas that we were using here. These guys are both of our half-angle trig identities. So this is the cosine half-angle identity and the sine half-angle identity. Now, as a side note, recall that if we were doing trig 2, it was basically rewrite everything, simplify, and then see where to go from there. Sometimes we might need to repeat trig 1, sometimes we might need to repeat trig 2. It depends on the problem. And just as a recap, I'll do an example here, along with a comment for you guys, because sometimes these tricks aren't quite so obvious or cut and dry. Sometimes it might, be useful to simplify before you try to tackle your integral. Like in this particular case, I'm giving you guys the integral of cosine squared of x times tangent cubed of x. You will notice that this doesn't technically fall under any of the tricks that we've been using, because we have a cosine term, but we also have a tangent term, and tangent is not explicitly sine or cosine. However, if we simplify, we can rewrite it in terms of sine and cosine, right? Hopefully we recognize, I'll copy over this beginning part, but hopefully we recognize that tangent is the same thing as sine divided by cosine. Since tangent was cubed, that means that both of these guys are going to also be cubed. And this is an integral that we can clean up a little bit, but it is written in terms of sines and cosines, right? If I clean this up a little bit, probably a fast observation we can make is that all the cosines here, we don't need to keep all of them. Some of these can be canceled out. So I can view this as a sine cubed over cosine integral. So at this point, everything's written in terms of sines and cosines. Hopefully we recognize everything here is to an odd power, so this should fall under the category of trig 1, right? I see odd powers. I probably want to save something for a du. What do I save? Now, I've showed you guys a couple examples. I scroll down a little bit to give myself some more room. I've showed you guys a couple examples where if you have multiple of these things to odd powers, it doesn't really matter which one you pick. However, here, there is a better choice. If I tried to save a cosine here, cosine's actually in the denominator. If I try to save that and attach it to the dx, what I'm really saving is a 1 over cosine of x dx. I would actually be saving a secant term in that case, and that is not what I want. So instead, if I'm going to apply, my trick number 1 here with the 3 steps that I gave you guys, step 1 was going to be to save a term. I've just made an argument that it's better to save my sine term. I'm going to go ahead and do that. Okay? So I will go ahead and save a sine of x dx. Alright, once I have saved that, the next thing that we said that we wanted to do was go ahead and rewrite my rest of my integral in terms of the opposing trig term. Since I saved a sine, that means that I want to make sure that everything else is written in terms of cosine. So that means the problematic part of this integral is actually this numerator. I'm going to need to find a way to rewrite that in terms of cosine. Now, if we remember our trig identities, okay, I had this on the previous page, sine squared plus cosine squared gives you 1 regardless of what angle you're taking those of. Sine squared, if I look at this equation, I should recognize that I can rewrite that numerator as 1 minus cosine squared of not theta of x, because we were working in terms of x. Now, if I do this at this point, I've rewritten all of the integral that I've needed to rewrite. My next step should be to actually perform a u substitution. So we've set ourselves up nicely for doing u as cosine of x. I'll scroll down and give myself a little bit more room here. That means my du should be negative sine of x dx. I will have to correct my coefficient a little bit here, make sure that I've got room to substitute stuff in. And if I do that, well, my integral at this point turns into 1 minus u squared over u times a negative du. Right, so negative 1 du. I'm going to clean this up a little bit before I actually get to anti-deriving. One thing I can do is multiply that through by negative 1. So this is going to change the order of some of my stuff here. If I distribute that through, I'll get a positive u squared and a negative 1. At this point, please don't try to directly anti-derive this as is. I don't want to see u cubed over 3 minus u over u squared over 2. That's not how this works. All of this stuff is combined in a quotient. We can't work with quotients. What we probably want to try to do is simplify, and if I try that, I'll get u minus 1 over u. Okay, if I divide everything in that numerator through by u, this is what I'm left with. So at this point I can do power rule and also apply my rule for natural log. And you don't want to finish out in terms of u. We finish out by actually substituting in whatever u we had decided to plug in. So this guy is going to be my final answer. Okay, I'll get a cosine squared term, a natural log of cosine term, and then since this was indefinite, I'll also get a plus c. Okay. Now, a comment that this, kind of raises, or a question that this raises, is the following. We just did one of these problems by, if we scroll up to look at what we started with, I had a cosine and a tangent here, so this wasn't written in terms of sines and cosines, but we did indeed simplify in order to tackle the problem using our current methods. Question, is this always the best thing to do? Well, let's see what happens if I try this. I've got this problem here in terms of tangents and secants. If I try to pull that same rewriting trick, let's see how it goes. We recognize the tangent is sine over cosine. I used that in my last problem. Since tangent is to the fourth, both of these things should be to the fourth. And then secant, well, the secant function is 1 over the cosine function, and since secant was to the 6th, that means that both of these pieces in the fraction should be to the 6th. 1 to the 6th is itself, but, cosine to the 6th we have to write as cosine to the 6th. At this point, I don't have to leave it this way. I can clean this up a little bit before I try fixing it using other methods. Looks like sine to the 4th over cosine to the 10th of x. And if I'm, taking a look at the powers that I have in this problem, you see that I have sine to the 4th, cosine to the 10th. Both of those guys are even, right? So here at this point, since I have, if I could spell correctly, even powers, well, this is gonna suggest that we try our, usual even powered method. Okay, so our trick for doing even powers was if you have some sort of number or quantity that's raised to an even number, you could interpret this as a square, okay, raised to some other power. In this particular case, that means that this would get written as sine squared x. That square is going to be squared. Cosine squared x goes in the denominator, but that is going to be raised to the 5th, because if I raise something squared to the 5th power, we would simplify that by multiplying to 10. Okay, so those are indeed the same things. And at this point, you could try to do your identities, right? So my next attempt would probably be my half angle identities, both of which look pretty similar. The only difference between the sine and cosine one was what power, okay? Or not what power, but what sign you have in the middle, right? So sine squared, this was a half times 1 minus cosine 2 theta, so cosine 2x here. Sine squared was being squared, so that whole thing is being squared. And down here, we've got 1 half times 1 plus cosine 2 theta, so in this case 2x. And since cosine squared was being raised to the 5th, that is being raised to the 5th. Hopefully you guys see where I was going with this. When I asked the question, is it always the best idea to write in terms of sines and cosines? Well, probably our next step was supposed to have been to simplify. I don't want to raise this thing to a square, or, this thing on the bottom to the 5th. I'm going to get some sort of weird hybrid polynomial trig looking thing, and basically this is just going to turn into a hot mess, okay? So the underlying idea is that the answer to that question is that it is indeed not always the best practice to try and attack it this way, right? So it is not always the best idea to rewrite your integral in terms of sines and cosines. Okay, we actually want to avoid doing it this way. That integral looks terrible. So this begs the question, are there other tricks that we can use? Well, I did promise you guys 2 more integral tricks in this lecture. First of them is going to be what I'll call trig integral trick number 3. The red flag for this is, shifted that down a little bit. Red flag for this is as follows. My integral has to be written in terms of secants and tangents, with your secant to an even power that is greater than or equal to 2. Okay? A comment, we're not going over explicitly what happens if you do integrals in terms of cosecants and cotangents, but I will give you guys the warning that if you did encounter one of those, it would basically mirror this trick exactly. Just replace every instance of the word cosecant, or secant with the word cosecant, and every instance of the word tangent with the word cotangent. You would get a trick that would be totally valid. But just because they look so similar, I'm not going to focus on that. Okay, we'll just roll all of that into trick number 3. At any rate, if you see one of these secant and tangent integrals and you've got an even secant power, here's what you do. We are going to mirror the method that we used in trick 1. And what I mean by that is we are still setting aside some sort of a term to use as a du. Since we are using that as a du, it's going to suggest a particular u, namely if you have a secant squared for a du, you will probably want u to be tangent. So that's going to suggest that you want the rest of your integral written in terms of tangent. This is why we have step 2. And then once you have your integral set up that way, you are basically building yourself a good situation to do a u substitution with the tangent function. Now, a comment, I've kind of just said, hey, rewrite the rest of the, well, what did I do here? Into integral. Okay, sorry about that. I was a little bit fast when I was going over my slides earlier. Edit correction. Anyway, I was a little bit fast on step 2 here when I said just rewrite the rest of the integral. Like, hey, how do I do that? We're using more trig identities, right? So I will go ahead and make a comment, what trig identity do I use on step 2? Well, let me scroll down here and give myself a little bit more room. We obviously can't use the old identity, right? I can't use sine squared theta plus cosine squared theta equals 1, because this particular trick, we have just said that it has to be written in terms of secants and tangents, so I will not see any of those here. Well, there are a couple ways that you can change up this identity, and one of those is you can get a totally different identity back if I divide through by, well, here let's just try cosine. Okay, if I divide everything in this equation through by specifically cosine squared, well, here I'm dividing through by cosine squared, here I'm dividing through by cosine squared. This is going to give me a new identity. It'll look like tangent squared theta, because sine over cosine is tangent, plus 1, because anything divided by itself is 1. And this is going to equal secant squared theta, because 1 over cosine is secant. So, another thing that we're going to need to know in this section is this identity, right? Most of you guys are probably pretty comfortable with the sine squared theta plus cosine squared theta one. This is just a minor change to that, right? So we'll need to know this identity, that tangent squared theta plus 1 is secant squared. We are going to use this whenever we need to rewrite our integral. So up here, where I mentioned step 2, we wanted to rewrite our integral in terms of tangent. Sorry for a moment, this is kind of bugging me. If I want to rewrite stuff in terms of tangent, well, anytime that I see a secant squared, I'm going to replace it with tangent squared plus 1. Okay? So, let's go ahead and try that, right? I'll pull up this example here. This is the same exact one that I tried before that turned into a hot mess. Let's see if we can tackle this again using this new identity, right? So, again, the thing that I'm going to be using is not sine squared plus cosine squared gives me 1. It is going to be that tangent squared theta plus 1 gives me secant squared. Okay, so I'll keep that in mind for later. All right, let's try this, right? Step 1 is, once I've recognized that I've got this integral that falls into my previous pattern, we have a secant written to an even power that is greater than or equal to 2, and this integral that has nothing but tangents and secants in it, I get to apply trick 3. And trick 3 is telling me on step 1 to save a couple of those secant terms for a du. Okay, so much like before, we'll copy over most of this problem, but I do have to split apart this secant term. Okay, so this on the end is what I'm saving for my du. Okay, that bit gets saved. Now, my next step was that if that was what I was saving for du and I'm ultimately shooting for a tangent u substitution, I have to write everything in the rest of my integrand in terms of tangent. That means that this middle part, the secant to the fourth term, that's a problem because it's not written in terms of tangent. That is the thing that I'm going to need to rewrite with this trig identity over here on the far end. So, for me to use that secant squared identity, I'm going to have to write this so that there actually are secant squareds appearing somewhere. We can use that power trick that we've run into a couple times before. I can interpret secant to the fourth as secant squared. I'm still saving this business on the end for a du. And at this point, it's a little bit easier for me to substitute in my identity, right? We've said that secant squared is the same exact thing as tangent squared plus 1. I've still got this thing on the end. And at this point, I have set myself up very nicely to do step 3, which is a u substitution involving a tangent function. Okay? I'm going to scroll down to give myself just a little bit more room. This is going to suggest that my du is secant squared of x because your du comes from deriving your u and slapping a dx on the end. This means that when I do my integral substitution, I no longer have tangent to the fourth, I have u to the fourth. I no longer have tangent squared of x plus 1, I now have u squared plus 1. And I no longer have a secant squared of x dx on the end, I now have a du on the end. This is not an integral that we want to go ahead and take directly. Okay, do not turn this into u to the 5th over 5 and u cubed over 3 and u. Don't do that. There was a product, there was a composition here. The composition does not suggest that we want to do another u substitution because, you know, if u is a square, du would be a linear term. We don't have a leftover linear term. We have a leftover fourth power. The better way to handle this is to try and simplify this out before you antiderive. So first things first, I'm going to FOIL this square out. It'll give me u to the fourth plus 2u squared plus 1. Next, I'm going to distribute that power through. So this is going to turn into u to the 8th plus 2u to the 6th plus u to the 4th. Remember, when you're multiplying two powers with the same base, you add powers. And at this point, you can actually go ahead and take an antiderivative, right? So I will get u to the 9th over 9 plus 2u to the 7th over 7. So 2/7 u to the 7th is another way to write that. And then I'll add u to the 5th over 5. And not forget that this was an indefinite integral, so I have a plus c. Final step in tackling this is to make sure that you substitute your u back in. So these u's are going to all turn into tangent terms. Okay, so all the way across the board here, I'm going to start seeing tangent terms. Okay, so that'll give me my final answer here. Okay. This is not the only integral trick that we're going to run into. I will note that there is another one, and this is the last integral trick that we will see. Remember, the last case had us looking at integrals of secants and tangents where you had a secant to an even power. This trick, the red flag is instead going to be that we have our integrand, a secant and tangent integral, with tangent to an odd power. Okay, so the other function to an odd power. And it's also helpful if there's at least one secant term floating around. Hopefully we can kind of see where this is going. This is also modeled after trick number 1, in that this is one of those save a du kind of tricks. Okay, we've seen that in trick number 1, those were geared towards u substitution with sine or cosine. Last trick, trick number 3, was geared towards a u substitution with u equals tangent. This is going to be geared towards u equals secant. So if it's geared towards a u being secant, your du is probably going to be a secant tangent term. Okay, so this is why we wanted tangent to an odd power and for there to be a secant term around, we need something to pull out that du. Now, the idea is that if that was going to be our du, again, we probably want to do a u substitution with secant, so we want to rewrite the rest of the integrand in terms of secant. And after we do that, we can actually do our u substitution with u equals secant. Now we'll scroll down a little bit just to make this friendly reminder here. Please, please, please do not forget the identity that we are using in this particular case to tackle this problem is that tangent squared plus 1 theta plus 1 is equal to secant squared theta. So if I'm trying to rewrite stuff in terms of secant, probably what we're going to end up using is the following. You know, if you solve for tangent squared in this identity, that means that that's going to be equal to secant squared theta minus 1. So anytime that you see a tangent squared expression in one of these problems, this is how we're going to rewrite it. It is going to turn into a secant squared theta minus 1. Okay, so that's what I'm implying that we are going to use on step 2. Okay, that's how we're rewriting stuff here. Okay, so let's see if we can try one of those. I have a tangent cubed of 2x times secant of 2x dx. We will recognize that tangent is indeed to an odd power, so trick number 4 applies. What we said that we were going to do for trick number 4 was to save a secant tangent term, so I will go ahead and do that. If I pull out one of these tangents, that leaves 2 of them left. Okay, but I have pulled out one of those tangents to leave myself with a secant tangent term. Okay, that's this thing on the end here. That's what I'm trying to save for my du. Again, the idea is that if I'm saving this for a du, I probably want my u to be some sort of a secant function, because that would derive to a secant tangent term. So that means that I want the rest of my integral to be in terms of secant, and it is not, right? This is not in terms of secant right now. So what I'm going to go ahead and do is rewrite this. Again, we had said that the identity that I'm going to be using here, the identity that I need, is that my tangent squared plus 1 gives me a secant squared. If I use that identity to substitute out the rest of this expression, this is suggesting that that tangent squared term should turn into a secant squared minus 1 term. So this is going to be secant squared 2x minus 1. Okay, that's me performing my rewrite. And I'm going to leave the rest of this exactly as it is. Okay, so this thing is being saved for the du, and then the rest of this we are hopefully going to set up with a nice u substitution, ideally with my u being some sort of a secant term, right? So again, you know, if I derive this, your derivative of this is going to be 2 times secant of 2x tangent of 2x dx. I don't actually see any 2's there, so if you want to do the coefficient correction where you get a half du is secant of 2x tangent of 2x, that's great. But again, to really emphasize here, we had said that we were saving this expression towards the end of your problem for du. Please be careful in substituting things in. The reason that I underlined this here was to emphasize the bits that are being saved, right? So when I say that I'm saving it for a du, I'm not trying to substitute any u's into any of this. So be careful when you're substituting in, because I will let myself replace any secants that I see in the problem with u, except for the stuff at the end. Right, so this beginning secant squared of 2x, sure, that's going to turn into a u squared instead. But, you know, this secant of 2x term, right here, do not replace that with a u. Okay, that does not get replaced with a u because we had said that we are trying to save it. We are hanging on to it so that we can actually substitute in my du expression here, right? These guys are the same thing. So the bit on the end in my integral, rather than me writing, u squared minus 1 quantity times u, etc., make sure that that initial secant squared, or not secant squared, but that, initial secant of 2x bit, this part does not get replaced with u. That whole thing is getting replaced by a 1/2 du, okay, just like we said in the line above. So I'm going to scroll down to let myself have a little bit more room here. If I go to clean this up before I integrate it, I've got a 1/2 u squared minus a 1/2. This anti-derives with power rule, in a pretty straightforward way. If I want to, at this point, I can go ahead and substitute my u back in. We said u was the secant term. I'll clean up my coefficient at the same time. This first piece, I've got a secant cubed of 2x. And in this second piece, I've just got a secant of 2x. Okay, so this is going to be our final answer for the problem. Okay, I'll do one more example. One more of these. Just as a note, sometimes it isn't the most useful to try and fall into a method explicitly with what I've given you guys. Think of these tricks as more loose guidelines than anything else that are going to be helpful tools rather than these are the only ways to do trig integrals. They aren't. So sometimes, yeah, the tricks are going to be useful, and a lot of the integrals that y'all are thrown are going to be useful to handle in that manner, but sometimes it's nice to just think a little bit about the trig identities that you're using or that might apply to your situation. So in this particular example, the reason that I highlight that is this. If I'm just strictly looking at this example in terms of trick 1, trick 2, etc., etc., the one we know how to anti-derive, but the tangent squared becomes problematic, right? It is not written in terms of sines and cosines. If you try to split it up in terms of sines and cosines and do any of those tricks, we've seen before how the even-powered things get nasty really fast, so we probably want to avoid trick 1 and trick 2. If I was thinking about one of the latter tricks, well, remember, we only get to do trick 3 if there are secant squared terms that we can pull out. Okay, there's no even secant powers here, so trick 3 fails. And trick 4 only works if, we have secants and tangents, and, tangent has to be at an odd power, and it's not, so none of these work. But if I'm a little bit clever about this and I'm thinking about some of my trig identities instead, we have already noted, in our usual identity, tangent squared of theta plus 1 should give me secant squared of theta. This is the identity I had you guys use for the last couple examples. That means that I can turn this guy into a secant squared integral, maybe not secant squared theta, but secant squared x. And that's actually a basic rule for us, right? So sometimes it pays to be, a little bit thoughtful with some of your trig identities rather than it is trying to brute force stuff into a method. So do be on the lookout for that. Okay? I will close this on a question for you guys to give me at some point. This particular question, there are, I will warn, multiple ways that you can do this one. So, if you guys want, we can tackle this in any of a number of ways, and it's totally fine. I can think of probably like 3 or so different ways that this can be approached, especially in the context of what we've talked about together. Whichever one you guys want to pick, go for it, right? So there's a number of different ways that y'all can come about answers to this using the methods that we've gone over today and, during the last lecture. If you guys have questions, on this lecture, on this quiz, on stuff related to the homework. The homework for the section is posted already, by the way. Feel free to let me know. If you guys want to talk stuff over in person, I'm welcome to doing that too. Okay, I can always hold off and wait to take the quiz until you've gotten your questions out of your system, but do feel free to ask about stuff that you're stuck on. If you have work that you've tried and there's a point that you're really hung up on, send me a picture, okay? Ask me what's going on. I can try to give you guys feedback. And hopefully we can get this taken care of at some point once we're back from the storm. As usual, till next time, guys.